Yeah, hi everyone. I can't believe Dave's talking at the same time I am. I'm gutted. This is twice now this has happened to me. So thanks for coming to my talk. I appreciate it. I would also rather be in the next room too. So a little about me. Hi. I know a lot of these faces in the room. If you don't know me, my name is Harriet. I'm a software engineer. As Emma's just mentioned, I work on the iZotope team at Native Instruments. You might know that I worked on C major before that. I've been there for about 2 years now. It's literally nearly to the week because I started just after ADC a few years ago. I have a bit of a DSP ML focus. Again, as Emma has already mentioned, I am a DSP nerd. I just like the maths of it all. In another life, I was a guitarist, performer and doing that. And I can pronounce Cynefin correctly. I'm calling everyone out. It's Cynefin. We don't have V's in the Welsh alphabet. That's why it's an F. The Venn diagram of C++ developer and Welsh person is slim, so I'm glad that that word comes into my day-to-day life. So let's just talk about reverbs quickly, because our legacy code is based in reverbs. These are some good resources. I would implore you all to take a picture of this slide if you want to. If there's one thing I would read from this slide, it's the reverb bid. It's the most important one here. So when you're thinking of a reverb, what are you thinking of? This is a cathedral. You're thinking of the persistence of sound, right? Or a signal like after it's been produced. So natural reverb happens in cathedrals such as this because the sound is bouncing everywhere. You know, this chap's jacket down here might catch something. Everyone's voices might go in different directions. But the idea is that you've got a natural reverb because cathedrals are large and they're good places to see this. If you zoom in on this photo as well, you get 2018 me singing Mozart's Requiem for the first time in the alto section. And my voice is getting bounced everywhere. It was a great experience. 10 out of 10 would recommend. We've been mimicking this for decades, like decades and decades. This is a modern reverb chamber, and it's common to have rooms or like legendary rooms that people will play a signal and place posh mics to hear it back and use these sort of nicely padded spaces to get the sound that you want. But this is like a whole room in Abbey Road Studios, and that's not something everyone can do. So here's a really early example that is on reverb right now, if anyone's got a spare $5,000. This is an EMT 140 plate reverb, and this is from 1957, 1958. I'm not sure exactly which year it was. And this is using electromechanical transducer. So this is creating vibrations in this rather large plate. And a pickup captures that vibration, and then the resulting signal is reverbed. And this is a very early one. If we jump forward a little bit in digital audio context, you might take a reverb by capturing an impulse response. So I love this photo because apparently when you do an impulse response, you get a gun and a hat. So you don't have to use a gun to do an impulse response. You can use a sine sweep, you can clap, you can use any form of fancy tools. The idea is you're making an impulse. You're making a loud noise that you can detect with a microphone or an array of microphones, and you're getting these natural bounces. And then you can convolve it, and this is the most maths I promise we'll do today, where H is the convolve. Your resultant signal will sound like it was in the room. Fantastic. That's great. This is a perhaps very popular example, early example is Altiverb, where people share impulse responses on forums and such like this. Altiverb has monopolized this in a way that's quite useful. Convolution happens in non-reverb contexts as well. You might see it in iZotope Trash. We have a convolve module, does the same thing, of course. This is the inside of Boston Symphony Hall. I've never been, never had the pleasure. This is you inside Boston Symphony Hall. You've bought yourself a very nice seat there, and you've brought yourself a microphone. You've brought some way of making an impulse, be it a gun. Don't do that. That's a bad choice. And you've captured your impulse response. Fantastic. But now you've decided that you want to go sit in the eaves. You do the same thing. You make your impulse. You capture your impulse response. And now suddenly you're a conductor, and you do the same thing again. Right? You get a different impulse response, you're going to convolve it again. This is like 3 different ways of making a noise. And then to the non-audiophile in the room, you might say, oh, it just sounds like Boston Symphony Hall, right? So this is something I wanted to touch on because with an impulse response, you're sort of limiting where the microphone was placed at the time. When you think of an algorithmic reverb, you get to think of sort of the position in the room as an emergent feature. So you can decide where the person listening to your signal is sat. Inside Boston Symphony Hall, inside the Royal Albert Hall, wherever you like to be. So that's how I'd like to define algorithmic reverbs today. It's a reverb based on a mathematical model that simulates the physical space in some way. And when you say that, you can do whatever you want in terms of mathematical models, go crazy. But there are some terms that people have generally bound around so we can discuss things at conferences easier. You might see something like a reflection. This is a tap delay line. I believe there's a talk tomorrow that will go into more details about this. But it's essentially you're taking some taps, you're adding some gains, and what you're trying to do here is simulate the sounds of hitting walls, floors, etc., etc. And then you move on to the tail, which is like sort of a more diffuse way of bouncing signals. To model this, you might use a feedback loop of some form. And again, you will use gains and sort of band specify the frequencies or combos of the two generally. And then the diffusion. This is like, again, the more scattering of reflections. You'll generally have lower diffusion for regular rooms and then higher for big rooms. And that's all the reverb I want to talk today. This is a digital reverb unit from 1998. You can tell because it's brown. It's fantastic. This is a Lexicon piece. It's a Lexicon MPX 100. And in 1998, this was £250, which is incredible, right? Has anyone got one of these? Oh, incredible. Have you had it from 1998? That's fantastic. I'm sorry to give you an existential crisis. That's older than me. So if you've got one with dust on it, congratulations. So this is, you can think of Lexicon as a godfather of digital audio reverb. They're not the only ones, of course, but they are the focus of today's talk. Let's move forward. Let's go to Exponential Audio. This is a company founded by Michael Carnes in the 2010s. Michael Carnes worked at Lexicon prior to this. So the reverbs were based around the sort of designs of the hardware. Michael was famous for having stereo and surround plugins, and they're sort of very highly renowned in the post-production industry especially. So this is Michael Carnes. He's a musician, composer, engineer, maker of great things. Studied at Boston University, MIT, and is now retired from engineering completely. So I actually, unfortunately, never had a chance to chat to Michael before he retired. I've had the whole of 2 email exchanges before giving this talk, but I know he's watching today, so hello. We were under strict, no contact instructions from our product manager. The line was, Michael is retired, please let him be retired. Please respect that. But what he did do was leave us with a text that we call the Exponential Audio Bible. And this is full of trade secrets, so I cannot share it on screen today, I'm afraid. But it's an incredible read for any Native Instruments employees out there. It's incredible. He's an incredible orator, writer, and I thoroughly enjoyed his text. You can really tell he put all of his efforts into making these reverbs as believable and usable as possible. And Michael was with us all the way when we were porting this code. He was aware it was happening. He was, again, contact was reduced, but that was purposeful to not bother him, essentially. So Exponential was acquired by iZotope in 2019. We got given one monolithic repository containing all Exponential audio products. And that included all the third-party library dependencies that came with it. We did an M1 support update and a UI refresh in 2022, basically. So these were Michael's first-generation reverbs. I think I wanted to show them on screen because I love the sort of 2010s UIs of them all. So you've got Phoenix Verb and R2. These were the first ones that he worked on. Second generation, we moved to Nimbus and R4. And then we moved to Stratus. This is a next-generation reverb. It's quite pure, there's no notable modulation, and it's natural decay. The early reflections of this is similar to Phoenix Verb and R2, which is why I've tried to give you a bit of a context there. And this is Symphony. Very similar UIs, as you can tell, between the two. It's got a fat tail, It's more character. Modulation is a feature. There was a really fun chorusing junction in Symphony, and the ability to freeze a buffer in perpetuity, which was it was so fun to sort of look at that code and see how it was made. So after that, we get Equinox. This release this year, April 2025, and this combines both Stratus and Symphony in one plugin. Obviously, they're algorithmic reverbs, so we basically ported both DSP code bases and shared one UI for them both. So what does that look like? This is a really quick overview. There's a lot of controls. Again, algorithmic reverbs, you get a lot of control. That's part of the point. The main panel on the left-hand side, or I guess, yeah, left, my right, your left. This contains the most important settings. These are the ones where if you've pulled it up in a VST instance and you're playing with it in your DAW, these are the ones that you're going to hear the most change from, and obviously the reverb time and such will change. We've got a header which controls all of our preset selectors, our like balancing and unmasking DSP controls. The preset header in itself was an incredible feat. We've got additional controls here for attack, tail, early, and chorus. The chorus junction only enables during Symphony. And then we've got this fun EQ that is built with iZotope's EQ DSP. And then we've got some like dynamic controls where we've got some saturation, compression, and all that jazz. So it sort of follows your eye as you would read it. So what is legacy code? You search legacy code on Google, you'll get about 100 different answers. So I'm going to use it to say that it's code maintained by someone other than the original author. So in this case, Michael, when he wrote this code, was external to Native Instruments, to iZotope. He doesn't use our internal libraries or repositories, and this code is a little older now. Obviously, it was written, like, the handover was 6 years ago, and he's not aware of any code practices that we might follow. And this is what the README of our GitHub repo looks like. Very old school. We got delivered a thumb drive May the 1st, 2019, and it contained absolutely everything. So what did that look like? Very briefly, sorry if the text's too small here. This is one repository. I want to just make that clear. We've got all sorts of core infrastructures, 11 professional plugins that we could possibly make, and all the wrappers that we might need to build. What I'd like to draw attention to is the customized juice dependency that exists within this. So we think this fork originates from circa 2016 when you have a look at the blame and see where the commits come from. Michael added his own custom changes to surround sound routing. All of the then internal dependencies of Juice are frozen, and this led to a UI bug. Apple changed one of their APIs, and the long and short of it is when you instantiate a version of Stratus or Symphony and you have more than one instantiation in a plugin, you're seeing your CPU spike over to like 100%, and it was a really bad bug. Due to the complexity of the custom changes on top of Juice, we weren't able to just, move that dependency forwards. We weren't able to sort of go, okay, let's just update Juice. I literally found the commit where Jules fixed this bug and we were frozen. Zooming in a little bit, I want to focus on Stratus and Symphony, of course. The main thing to take from this graph is that there is a DSP library within this repo, and everything is shared between the two products. So there's a lot of sharing of classes of codes. There's a lot of base classes that are used in different ways. We cannot use this in its current form in any other product. So this will be locked to the code that we have with Exponential Audio. We cannot add tests. We can't use our current framework. And that's just, of course, the nature of the beast. You've bought some code, it will work how it works. So to summarize, we've got one monolithic repo, we have custom framework dependencies, and DSP shared between products within that repo. And what can you do with that? The temptation is to not touch the code, leave it as it is. It's working fine, we can still build it. And yeah, that's a choice. I love this comic. It just really made me chuckle when I was writing this. It's good to know that other people in other industries struggle with this as well. But the question is, how can we future-proof the DSP written by Michael Carnes? As I've mentioned, he put a lot of effort into making this DSP really sophisticated and applauded by the community. And, at the end of the day, there's a reason why iZotope spent money buying this. It's got its worth. So option one, continue building it as is. And that's what we did between 2019 and 2025. Obviously, there was a Juice contractor that came in to help us sort of start to unpick some of the dependencies of Juice. But we're left with the same things I was talking about before. We cannot use it in other products. The DSP is not compatible with the shared libraries for testing. And you are really dependent on certain team members understanding what's going on. You don't have like any sort of coherence around what's going on. Can you build it as a shared library? This is also possible. Lots of pros, lots of cons. I think what I would like to say is the reason we didn't do this is there's no user benefit to doing this. You're putting yourself in a position where you might have to deploy a DLL and have no clean DSP layer, but there's no benefit still to this. So option 3, extract the DSP into a new shared repository. Here are the pros and cons, you know. We can preserve the existing DSP. We can future-proof the technology. We can make all sorts of products with this DSP, and we can sort of like look at optimization routes and things such as that. And generally speaking, it's looked at by more devs, hopefully. No prizes for guessing that's what we did, of course. That's why I'm here. But you might be like, hold up, hang on a minute. If anyone here knows iZotope's plugins, which obviously you all do, of course. Wait, hang on a minute. Haven't you got 3 reverbs already? Yeah, we do. It's Dialog Match, Aurora, and Neoverb. We already have this. This started already. As you can see, it's called Phoenix Verb, and you might mention a few slides ago, that was the name of one of the plugins that Michael Carnes released. And this is a great example of poor naming of shared repositories, because Phoenix Verb was the first one that we ported. So now we just have a dependency called Phoenix Verb, and everyone gets confused. And as you can see, when I go back into the Git history, this started the week after iZotope acquired Exponential Audio. We were already trying to decide how we were going to future-proof the code, how we were going to share it between different products and use it in various places. And the key thing to remember about this is that these contributions have been happening for the last 6 or so years. Obviously, I've only been there for 2 years, so I'm only adding as to what's already there. But you already start to see that you've gone from one person to a whole sort of room of developers, and we're looking at the code, we're talking about the code, we're sort of talking about what might be best for certain things, and we're already sort of seeing this paradigm shift. When I was coming out with like a Miro board to talk about this, these were some of the things I wanted to talk about, and I thought it was a really good summary, actually. I think this explains well our approach to shared DSP repositories. You can utilize more C++ best practices because you're spending more time to look at it, of course. We had to create a bypass on our side. We'd never done a bypass such as that. We wanted to make aux outputs. What did we have? What do we need to audit to add to this? And yeah, this is a good summary. So this is an actual Slack message that I found when I was going through when I was writing this talk. And this was August 2024. So this was 9 months before we ended up releasing. And so I start about 4 hours before my Boston colleagues. So you can see I sent this at 10 to 4 because at that point I'd been staring at this repository like, oh my God, there is so much to do in so little time. And this is what this sort of looked like. Please don't take this to be gospel. I've not had the time to write a UML-based diagram, but this was sort of what we needed to do. None of this code at the time had been ported. And you can see there's a lot of shared, if you can see the arrows, there's a lot of shared bits between Stratus and Symphony because they are the next gen reverbs. So this was the game plan. We were like, let's get something we can send to beta. Let's start testing. So let's get Stratus ported first because we don't have to worry about a chorusing junction or things like that. Let's, as developers, let's talk, let's stand up every day. Let's try and divide the work class by class. Let's go and discuss the shared code as a team and decide on some sort of basic base class layouts. Let's add test coverage. That was really important. TDSP is our own internal usage of tests. And then we can sit back, relax, enjoy no bugs or misfortunes. It's as simple as that. And that's how this went. I have commits that look all over the code base that look like this. We would initially commit all of Michael Carnes' code, and then we'd make our custom changes on top, because then you get a really good diff of what you've actually changed. You can choose to see what you do. And also, we have C++ 17 now, so we can context for all the things, which is great. Something I wanted to note is that we're not trying to change any class structure within Stratus and Symphony. The goal is to keep all these quirks and features of the code. Something that came through when we were talking to professional users was that they don't want things to change, they want things to sound the same, and they want everything that comes with it. This actually, in fact, acted as an engine of discussion at iZotope, and we could talk around design patterns, and it sort of opened up another way of looking at how we might do things. And I really enjoyed that as a sort of a newer member of the team. It meant that I got to be like, but why do we do things like this? Like, if Michael's done it like this, could we do that? So yeah, I would implore you to do such things. Look at other people's code and sort of think about what you can take away from it. So this is what we did. We went through, we went class by class. We tried to keep things as simple as possible. But one thing I would like to draw attention to is a code adjustment we made. I think it's from Michael's hardware days. He was very keen on optimization. I guess he had, minimal computation power. And reading his notes back, you can really see how important it was to reduce CPU load as much as possible. When we talk to our post-production users, this is also important to them because they might have hundreds of instances of plugins that they're using. It might not be as applicable to some producers, but it can become important. So when I talk about loop unrolling today, I want to think more about auto-vectorization. We know it's beneficial, and it's something that compilers are very good at. There can be other instruction bottlenecks, of course, but we should use auto-vectorization where possible. And the TLDR, the long and short of it is, we will take something that looks like this from Michael Carnes' code, where he's written out different vector sizes in a switch statement to sort of try and absolutely optimize whatever he can out of his fixed size loop unrolling. And we turn it into a templated thing like this. So in our port, we rather chose to pipe the sample rate down from the top level class as like a constructor argument, and we can assume a constant vector size, which is defined in the constants file essentially. This template approach gives the compiler all the information it needs. Compile time to unroll loops. It inlines code, can use SIMD. This can result in faster, more efficient DSP code and less overhead than a switch case approach. And here's a big chart of pros and cons. I think the one I would like to highlight is that we were trying to reduce the amount of lines of code we needed to maintain. This was key. We want to keep the DSP sounding the same, of course, but if we can reduce what we have to look at, fantastic. I do want to leave you with an example to play with. If anyone attended Elis's talk before this, I think tinkering is super important. It's something that I love to do. That's why I co-run a C++ group, so I can do this stuff. It's interesting to see with what optimization flags things will unroll. So instruct the compiler to do advanced loop unrolling and have a look at the assembly. You'll see the benefit. So let's go back to our timeline. So this is how we did things from August to March. We were porting, but at the same time, we were making a new plugin. We were making Equinox, and I had the joy of actually doing the first PR that merged to make this. So that was fun. We had a lot of chatting. We discussed how we could edit inheritance of a few classes, because some of the classes were hundreds of lines or thousands of lines of code long. So we made some new classes just so things were even more modular. We wrote a lot of unit tests. That was something I was keen on. And this took a lot of time. We overran, I've written in my notes a little, we overran a lot. I think I was discussing this with Roth, one of my managers, and he was like, oh, I knew you were gonna run. And I was like, did you? Why didn't you tell me? And he was like, yeah, you can't, you know you're gonna overrun, and then you overrun even more. And I was like, okay, cool, great. I'm glad that everyone else was aware of it. But by March, the reason I call that out is because we start having a plugin that looks like our final plugin, essentially. And we have, at this point, Stratus and Symphony in one plugin. We started adding our own DSP libraries to this. So we've got adaptive unmasking here. This is, you can see in this beta, I actually got the color of the differential line wrong. So that was great. But I got that right in the polish pass, so it's all good. We've got this placeholder UI. This is what the DSP might look like. We were going back and forth on how we might port Stratus and Symphony into it, and this sort of seemed to be the way we decided upon. And you remember the earlier slide where I was like, sit back and relax? And the bugs started coming in, unfortunately, from beta. This was a really interesting bug to start to look at. Our tail's crackling. Big shout out to our QA for having the ears of angels and starting to like diagnose where this might be, giving no context to the code base. So this is our ticket, natural algorithms crackling at high reverb times with large or small size. And it's like, oh my gosh, this was March. We released in April. And we were like, oh no, where do we even start? But so natural algorithms we knew were Stratus specific because that was our sort of naming term. So we knew we were looking in the Stratus code base. It occurs reliably with a reverb size set to max or min, and reverb time set to max, essentially. What we started to do was turn down other parts of the DSP. So turning down early reflection levels made this crackling in the tail more obvious. So we started using the tools that were available to us. This looked like loading RX. We were wave dumping out the tail because, if you remember earlier, we said we were trying to make it more blocky. We could like spit bits out. So we were able to spit out the tail and you can see these high energy spots everywhere. And we were like, oh no. The long and short of it was, in some reverb modes, the gain could surpass 1. This didn't differ from the original code. So we were suddenly stuck with this sort of thought process of, well, is this a feature or a bug? Do our pro users in their post-production studios want this crackling or not? And if you go back and look at the code from Michael Carnes, you can actually see comments he left for himself where he was trying to fix this himself. So armed with that knowledge and all the sort of debug compile code he left himself, we were pretty confident to say that he did in fact want this fixed. So you had to sort of make a trade-off here between, are you changing the essence of the reverb or are you fixing a bug? So we count the gains, essentially. If in doubt, stud max error, right? The high energy remains in places, but we were like, hey, this is a good trade-off. This is a feature now. And it felt like the right move. I will also, again, mention this was coming in hot for our release date, so we didn't have time to troubleshoot anything more advanced at that time. And this is just one example of bugs that were actually a feature. We made various calls to go one way or another way when doing this. And a lot of this is like very little change to the outputted reverb sound at all. It's just because we were able to output specific parts of the reverb to RX, we could look at these frequencies and see what was going on. And then boom, April 2025, Equinox launches. There it is, in its lovely YouTube depictor. After delay, we were able to launch it to the world. The legacy code takes a while with due process and care to port, of course, but I'm pretty comfortable with how it came out. So what did we achieve? We built a reverb plugin, of course. We ported legacy reverbs from 2 different engines. We made one UI for them, and it's seamless. It's totally seamless between the two. So like the reverb time, you'll notice that one is the big one. It will change depending on which one you're in. There were thousands of presets to port over, so that's what we had to do. We actually had to extend our multi-channel config support, so that pushed us forward into all these like 7.x.2.6, 9.x.4, etc., all that jazz. We then decided to add our own EQ and adaptive and masking tech because we were trying to take an angle of, well, how can we make this have new value? Like, why do we want people to buy this? What does it do? And there were like numerous other improvements that we made as well. I don't have time to go into it today, but I remember writing a class around seeded deterministic randomness. So come and talk to me about that if that's interesting to you guys. We stabilized some exploding filters as well. We had to implement like a lattice filter at one point, and we did also manage to save legacy sessions. So people who were cross-grading up to Equinox can save their old legacy sessions that have Stratus and Symphony. We have now retired those 2 plugins. We cannot maintain Juice in that sort of form as it was, but we've kept the DSP alive and we've future-proofed it for in the DSP repository. So that's what we did. Thank you very much for listening, and thank you to all my talk collaborators. I'll be taking questions. Thanks.